Hi everybody, this is David. I'll introduce Rick here in just a moment, but we're going to talk about closed circuit desalination. I think you'll find it very unique. There's going to be a 40-minute presentation. I'll give a short intro, maybe 10 minutes, and then Rick will give details on the CCD technology, and then there will be 20 minutes of Q&A. So if you would type your questions into the questions box, and then during the Q&A session, Rick will handle the questions. So this presentation is recorded and will be available on our website. You'll also receive an email tomorrow that will give you this URL. And you'll also, in the thank you email tomorrow, you'll receive a PDF of this presentation. So again, thanks a lot for being here. So just to make sure you understand, David H. Paul Inc. and Desalitech Inc. do not have a financial relationship. DHP is not promoting this technology. We want to just make sure that you're aware of this technology because it is unique and it's another option for high recovery. And that high recovery in today's world equates mainly to water and wastewater minimization. So just briefly, I've been in RO water treatment for a long time. Been trained and consulting in hundreds of plants since 1988. I have a Master's of Science degree in microbiology. Rick, great guy. He's done a lot in his 25 years. He's been VP of a couple of other companies, other technologies. He holds several patents on desalination methods and devices, and he has a PhD in chemical engineering. Okay, so let's start out by putting into context the CCD technology. What is different about it? So that we can compare CCD to RO, let's take a look at the challenges of conventional RO units for high recovery applications. And the most important ones, for the first one, typically going to require 3 or 4 stages. Now you're going to see that CCD only has one stage. In all conventional RO units, the first element is going to be the highest fouling element because it has the highest water flux rate. And water flux being the gallons of permeate per square foot of membrane per day, or liters of permeate per square meter of membrane per hour, whether we're talking about American units or metric units. Also, the more elements that you put into a pressure vessel, the higher the pressure drop, which then means that the first element will have proportionally even higher pressure, so higher water flux and higher fouling rate. So again, we'll see that CCD technology typically only has 4 membrane elements, sometimes 3. And then the other factor that affects fouling is the cross-flow rate. Cross-flow is the feed concentrate flow rate. And when I use the term concentrate, 2 other terms are reject or brine, all 3 of those mean the same. But the feed brine, feed reject, feed concentrate flow rate, that is the flow rate of water that goes across the surface of the membrane and kind of washes things off the surface of the membrane. So if we look at a conventional RO unit, we may see that the average water flux, so here's gallons per square foot of membrane per day, here's liter per square meter of membrane per hour, that the average may be in a reasonable range, but then when we look at the first membrane element, the water flux rate is extremely high, and the last membrane element is relatively doing very little. So this is something that we find all the time in some of today's RO units. Well, there are 3 things that we commonly do today to reduce the first element fouling rate, reduce the water flux rate of the first element. 3 ways: hybrid elements, first stage permeate back pressure, and interstage booster pump. So here just an illustration that we've put low permeability, high salt rejection membranes in the first two positions in this case, and then the rest of the membrane elements are higher permeability, higher water permeability, lower salt rejection membranes. So this then forces water to go more downstream of these first two elements, so it reduces the water flux rate on the first element. It's kind of challenging to really get the two stages to look the same. Here we can see the same types of water flux rate using hybrid elements, also called internally staged elements. But you can do it with permeate back pressure. So the first stage permeate back pressure, here's permeate coming off. We put a back pressure on. That will force less water through the membrane in the first stage and push the water into the second stage. So you really can, using this, you can get the two stages to be very similar. You can do exactly the same thing with an interstage booster pump. All right, so let's take a look at the CCD technology. Rick will give you more details. I just want to give you the real fundamentals and the unique features. So one stage, no matter how high the recovery. So we talked about, if you want to go to 90%, 95% recovery with conventional, you'd be at 3 or 4 stages. Well, with CCD, only one stage. It's a semi-batch mode. 90% of the time, you're operating at 100% recovery, and only 10% of the time are you dumping the reject. Only 3 to 4 membrane elements per pressure vessel, typically 4. Variable controlled cross-flow rate, variable controlled recovery rate. So here is a pressure vessel, and it has 4 membrane elements in the pressure vessel, has the standard high pressure pump feeding it. But here's a big difference, is now the concentrate brine or reject from the pressure vessel will go to a circulation pump, in this case showing a 3-way valve, and this is going to recirculate. So this is going to give very high cross-flow rates to reduce fouling and scaling potentials. And then while you're in operation doing this recirculation, the water is going to get more and more concentrated until when it hits the point that you've achieved the percent recovery that you want, then it's going to go from this closed circuit recirculation mode into the brine dump. So we're looking down here now. So 90% of the time in closed circuit, 10% of the time in the brine dump. So now the 3-way valve is going to change. The brine is going to be exiting to wherever it goes to drain or to downstream treatment. The feed water then pushes the concentrated brine out and then goes to drain. So this is called the high recovery brackish water RO system, reflex system. But also there's a low recovery, like for seawater RO, low recovery, the Reflex Max, where you start out exactly the same way. So we're circulating, we're recirculating, we're going to concentrate. But now, because we're talking about high energy, we really need to recover that energy. So there's going to be a side conduit that's going to act as an energy recovery device. So while we're circulating, we're concentrating, and then when it gets to the percent recovery that we want, gets the concentration that we want, then the valve's going to change, and now the brine is going to be going into the side conduit, pushing feed water up into the closed circuit pressure vessel, and this feed water is going to be pushing the brine out. Once the brine has pushed all the feed water out, now we're back in closed circuit mode, and now the feed water is going to push the brine to drain. So very similar to a positive displacement energy recovery device. Okay, so that's just a rundown on an introduction on CCD. Now Rick is going to give the bulk of the presentation now, the details of CCD. So we're going to change presenters, and Rick will come on in just a few seconds.
Okay, I'm going to go ahead and roll, presuming everyone can see the presentation at this point, and hopefully the audio is okay. Well, thank you, David. This is really a pleasure. As David said, we've known each other for quite some time. We have a lot of respect for David's work and the training and provided by DHP. These guys are really stay on the edge of what's new in desalination water treatment in general, and we're just thrilled to be included here in his overall presentation of the state of the art. And we'll dive right in here to Desalitech's process and experience. So I'll start with a few quick slides about why we do what we're doing. The real motivation is that the world is running out of conventional water supplies, fresh water supplies. And if you look in the developed world, industry is the biggest consumer of fresh water. And that's expected to increase much more rapidly than the increasing freshwater consumption for residential use, for example. So Desalitech targets industrial applications, and we're committed to high efficiency water treatment for both water purification, reuse, and for desalination. So, and in so doing, we're making new sustainable sources of water available. Okay, I'll talk about the Desalitech process, but what we're bringing in terms of value proposition is a pretty significant increase in recovery rate. So, and that has a benefit of making the most use out of water resources and reducing the amount of concentrate reject produced by an RO system. We're able to cut energy consumption pretty substantially. Our systems resist fouling and scaling, and that enhances their reliability. And they offer flexibility at a level of flexibility that is just impossible with traditional RO systems and platforms. This is a chart published by Global Water Intelligence. It shows that Desalitech is doing well in terms of moving toward the plateau of productivity that now you find traditional RO and thermal desalination methods on, for example. One of the reasons I like to show this chart is because a number of other new water technologies kind of coming up the curve behind Desalitech are focused on brine concentration. Almost all of those companies started out doing desalination and shifted their market focus to brine concentration, partly because it's pretty hard to compete with reverse osmosis, and especially hard to compete with high efficiency reverse osmosis that Desalitech is bringing to the market. So I'll talk about the motivation there, brine concentration, and why there's so many companies pursuing it. Here's some numbers around the cost of doing brackish or industrial water RO with a typical system for a typical lifetime. And the center numbers are at 75% recovery, which is pretty much the standard for industrial and brackish RO. And what you see is that the capital costs, the energy cost, and the operations and maintenance costs are actually less than 15% of the total cost of ownership, and that the biggest cost is the cost of water. So if you're operating at 75% recovery, you're throwing 25% of the feed water away, and disposing of that to the sewer has a cost. And also, that additional water that you're paying for or getting as feed add up to be at 87% of the typical cost of ownership for industrial and brackish RO. So now if you can raise recovery with this system to 93%, which I'll show you that we can, then you stand to cut your cost of ownership by 2/3. So there's a couple of examples of Desalitech customers. Coca-Cola's got a number of pretty large-scale systems. They're treating groundwater for actually use as an ingredient in Coca-Cola at a couple facilities. And then another customer, Mid-American Steel, they're treating a wastewater. The goal there is to just minimize the amount of wastewater that needs to be hauled off-site. Very quick payback because of their cost of disposal was so high, and they get to reuse the reclaimed water in their process. Here's some other case study installations, number of different industry verticals, power generation, food and beverage, consumer products, oil and gas. Okay, I'm going to talk now about technology and introduce that with these basic diagrams for what reverse osmosis is. And this is where you apply pressure to a salt solution, and fresh water is forced through a semi-permeable membrane. All the salts are held back. So you can't actually do it in the configuration shown on the left. You need to apply cross-flow. And that's illustrated on the right. So the feed and concentrate move past the membrane, sweeping away the boundary layer, the buildup of salts, and constantly refreshing that boundary layer, while permeate goes through the membrane. So cross-flow is essential for reverse osmosis and for nanofiltration as well. So now RO is well established. We've been doing it for years, 60 years, and things have improved. But Desalitech contends that things have not improved a lot, and that we've really reached a kind of a technological plateau until now. So this slide illustrates what I'm calling simple filtration. It's the kind of filtration you would do for multimedia filtration, for example, cartridge filters, your coffee filter. And what's happening here is a pump is pressurizing water against a filter. All the water is coming through. So this is 100% recovery operation. Every once in a while you either flush or change the filters, and so there may be some water loss associated with that change. But otherwise, essentially you can achieve unlimited recovery with a simple filtration. But as I showed in the previous slide, you can't do this with RO because you need cross-flow, and this is kind of a dead-end, not cross-flow configuration here. So here's how RO membranes are configured, and this is consistent with the illustration that David gave, which is if you need to go to more than about 50% recovery, you need to do that with multiple stages. And additional stages, you need to add some means to balance flux between stages. You can see this goes from 2 pressure vessels down to 1. If you go to 3 stages, then you're talking 4 vessels down to 2, down to 1. It adds complexity the more stages you add, and with that complexity, the system becomes less flexible toward changes in water, temperature, composition, etc. So, and what happens is if you lose control of the system, if it becomes unbalanced, you increase risk of fouling or scaling, or you just plain lose recovery. What Desalitech has done is essentially combined the simple filtration with the cross-flow reverse osmosis filtration. So what you see here is a diagram for what we call the reflex reverse osmosis process. A high-pressure pump feeds a membrane array, and now the concentrate is returned to the membrane feed. So it's brine recirculation. While it's operating like this, the brine valve is closed, so it's operating at 100% recovery. So all the water from the high-pressure pump is going through the membranes as permeate. Periodically, the brine valve is throttled open, allowing the concentrate to get pushed out of the system, and then it returns to closed-circuit operation. We've been able to achieve over 90%, up to 98% recovery in a single stage of membrane elements. Of course, how high you can go on recovery depends on water chemistry to some extent, and we'll talk a little bit about that. Fouling and scaling are limited by virtue of the cross-flow applied by the circulation pump and by the cycling. So these systems charge and then flush, feed flush a couple times an hour, sometimes 6 times an hour, and that's pretty frequent. That's frequent enough so that it limits scaling. So even if something supersaturates, we don't give it time to precipitate on the membrane surfaces. One of the main benefits of this system design is that with a single stage and with these basic components, which work for really any size system of any recovery rate, recovery, crossflow, and flux are independent. They can each be set at the control panel independently of the other. So you change recovery by changing when the brine valve opens. You change crossflow by changing the speed of the circulation pump. And you can change flux by changing the speed of the high pressure pump. I'll get into some data now on performance. This is a normalized flux. This is a side-by-side study of a Desalitech system with a traditional RO system in a wastewater application. So this is municipal effluent. And this is the apples-to-apples comparison. So everything was the same membrane, same water, same flux, same recovery rate. And what you see, the red line is the traditional RO that fouls instantly, and each one of those spikes is an attempt to do CIP and recover membrane performance. And they finally gave up. The Desalitech system not only resisted fouling better to start out with, but demonstrated full recovery of performance with CIP. So it works very well in water reuse applications where fouling is the main challenge. This is some data from an application that had a very high silica in the feed. The small numbers you see by the data points are the brine concentration of silica, which exceeds 900 parts per million. The normal saturation limit for this pH and water chemistry for silica is about 250 parts per million. So we've essentially 4 times supersaturated silica. And we were able to sustain this operation. And the reason is because this system flushed itself several times an hour. And then finally, energy savings. So what this illustrates is the green curve is the osmotic pressure curve, where a single stage RO unit would operate at a fixed pressure. That pressure needs to be high enough to overcome the osmotic pressure of the water at the tail elements. So if you add a second stage, follow the orange line, which steps up, and it starts with at the first stage, gets half the recovery done, and then bumps up pressure to the second stage to overcome the osmotic pressure for the other half. So CCD works like a highly multi-staged RO system. So you see the blue line there, and what it's doing is essentially hugging the osmotic pressure curve. So the pressure increases a little bit as the recovery increases through this cycle, and then it returns back to the feed composition again at the end of the cycle for a new cycle. So this is the way to reduce energy consumption. The energy savings is the area between those curves shown there. Okay. So I introduced the concept of energy savings partly because I want to talk about Desalitech's other process, the Reflex Max process that we apply to seawater RO and brine concentration. Generally, higher pressure, lower recovery applications. And what you see here is another cost of ownership breakdown for seawater RO. And here, energy is by far the largest contributor to the overall cost. So what we did with this analysis, we said, all right, what if you're able to increase energy efficiency in the RO by 5%? And if that was to cost you 1% of the overall cost of the plant, if you increased capital cost by 1% and saved 5% energy, would it be worth it? And the answer in this case is absolutely yes. You see a lower overall cost of ownership. So reducing energy consumption is the big driver here. So this is the Desalitech Reflex Max process. And again, David already showed an illustration of this, but it's the same basic process as before, as the reflex process with the high pressure pump and the recirculation loop. And now what we've done is added the side conduit. And so what the side conduit is then is that the pressure vessel that allows us to pre-pressurize feed and add it into the system when the brine is ejected from the system. So Reflex Max systems can operate at a broader recovery range, 40% all the way up to 98%, and they're good for higher pressure applications like seawater, up to 1200 psi or 83 bar. So this, if it works, little movie illustrates the dynamics of the Reflex Max process. You see an initial concentration in closed circuit operation. Then the side conduit is engaged, and the recirculation pump pushes the brine into the side chamber or the side conduit, and in turn, pressurized feed fills the membrane array. This goes through a couple of cycles, and again, concentration in closed loop operation, followed by displacement into the side conduit, and then the side conduit isolates again, and it's flushed out with low pressure feed water while desalination continues in the membrane loop. Right. So one of the attempts to save energy in seawater RO has been the introduction of high permeability membranes and all the research done on it. You may have heard about high flux membranes, graphene membranes, aquaporins, etc. All of these membranes are designed to be more permeable and therefore nominally require less energy for desalination. However, what happens with high permeability membranes is illustrated here. The dependent variable is flux. On the left, I show low permeability membranes, and what you see is from left to right, the lead or first membrane element in an array. To the right is the tail element. You see a decrease in flux. The reason is because at the lead element, your pressure is highest and your osmotic barrier is the lowest. And the tail elements, the pressure is the lowest and your osmotic barrier is the highest, so it has the least flux. Right, so go to a high permeability membrane, what happens is the water essentially drains out of the lead elements. So you get a significant elevation in flux of the lead elements and a depression in flux in the tail elements. If you have excess flux, you risk fouling. So David illustrated what he called hybrid elements and what's also known as internal staging. That involves putting in high rejection elements in the first few positions in the array. It pushes the flux back into the vessel. I illustrated on the right-hand figure here with the dotted line where you see suppressed flux on the lead elements and then higher flux in the tail elements. Well, with a short membrane array with 4 elements, which is what Desalitech processes typically use, you have a more limited flux distribution. One of the benefits for next generation membranes is that you can fill the pressure vessel with those high permeability membranes without as much risk of overfluxing and fouling the lead elements. All right, so let's talk about a specific example, operation of a Desalitech system under low energy conditions, but in typical conditions for seawater. So what we did was we operated at 47% recovery and 35,000 parts per million. It's close to seawater. So we got specific energy, which when normalized to 25 degrees C, which is kind of the standard way to do energy comparisons is in standard seawater, comes out to 1.45 kilowatt hours per cubic meter, or 5.5 kilowatt hours per 1,000 gallons. And if you've been working in seawater, you'll recognize that that's a very low energy number. State-of-the-art desal plants are consuming well over 2 kilowatt hours per cubic meter under similar conditions. So great potential here for saving energy in seawater installations of any size. So I want to summarize use of unconventional water resources is our future, and Desalitech believes that it behooves everyone for us to increase efficiency in our extraction of those resources. So our approach here can save 60% of the total cost of ownership by a combination of raising recovery, lowering energy, and increasing reliability and flexibility. We have standardized around system sizes for the industrial and brackish applications in the range of 50 to 1,200 gallons a minute. And at this point, we're working with a number of Fortune 500 companies and a number of applications around the world, but mostly in the U.S. and in Mexico, and that's because we're headquartered here near Boston, Massachusetts. All right, and with that, we look forward to responding to some questions. All right. Question here is Desalitech able to retrofit installed reverse osmosis unit? Desalitech systems are built with standard RO components, including membranes and pressure vessels and pumps. So nominally, it is possible to reconfigure an existing RO system to operate in this closed-circuit Desalitech design. However, it usually involves some compromises. For example, we really prefer 4 membrane elements in an array. Most installed RO systems have 6 or 7 membrane elements. So it takes some work, some field work to do a retrofit, but we have a number of retrofit systems operating. So another question here, what licensing and other fees are involved in utilizing Desalitech's technology? And do these vary based on system size? Okay, yeah, well, Desalitech mostly is a system integrator and supplier. So we supply complete turnkey RO systems with pre and post treatment as required. However, with our partners, we have a number of them, we do license the technology to them to build, and we are willing to license to others. So we're glad to chat with folks about that. And yes, generally the license fee goes with the value that the technology brings, and that typically scales with system size. So we have a license fee schedule that goes with the size of the RO system it's used with. Okay, question, what do we do with the brine or concentrate in our various applications? So reverse osmosis, well, something like 70% of manufacturing facilities purify their water, and the vast majority of them do it with reverse osmosis already. So with the concentrate that's generated from the RO, that can be discharged to the environment, discharged to the sewer, to an evaporation pond, to a deep well, or for additional processing, such as to an evaporator. So that's what's typically done now. You would do the same with the reject from a Desalitech process. You'd expect for that reject to be at a higher concentration, but nevertheless, the downstream brine concentration or treatment options are pretty similar. For most disposal, though, most brine disposal options, you pay by the gallon, or you pay by the flow rate. So it behooves you to concentrate that brine as much as you possibly can. Take, for example, our customer. I was saying that they were hauling their wastewater by operating an RO system at 90% recovery. They reduced that hauling by a factor of 10. Okay, is this system exclusive with Desalitech RO membranes? Good question. Now, Desalitech you can use any standard RO membrane or nanofiltration membrane in a Desalitech system. We like to say we're membrane agnostic. So generally we take our customers' direction as to what RO membranes they would like to use. All right, a question about what is the x-axis in the graphs on page 21. Let me look that up. Unfortunately, I don't have them. Oh, yes, I do have a number. Okay. X-axis is the, oh boy. I got a, oh, okay, I'm sorry. Yeah, position in the membrane array. So it's just a number. So the curves, the spots shown on the curve are the flux at each of the membrane elements going down the array. Can we address permeate water quality considerations? Okay. So, right. So generally speaking, permeate quality is dictated by the performance of the membranes. So if, for example, you have a 99.8% rejecting membrane, you'll generally get better permeate quality than with 96% rejection membrane. So the first order of what determines your permeate quality is the type of membrane you choose. Second would be how you operate the membranes. Generally speaking, the higher you drive the recovery rate, the more salt passage you get. Generally speaking, the higher the flux, the better permeate quality you get because you're driving more water through for a fixed salt passage. So, so permeate is both a matter of system design and of how it operates. Thankfully, because of good membrane projection tools, good membranes, reliable membranes, it's possible to predict before you build your system pretty closely what your permeate quality is going to be. And generally, the membrane manufacturers stand behind their projections in terms of the quality of permeate that you get. So across the board, RO membrane manufacturers certify the use of their membranes in Desalitech processes, and therefore we get the performance guarantees passed through from the suppliers. Okay, this feeds right into the great next question is how do we model our systems? We use membrane projection models like ROSA, IMS Design, Torre DS, Lua Plus, and Q Plus. I'm trying to remember the names and not discriminate against any of the membrane manufacturers, but we use the standard projection models. You need to do a couple of iterations because as of today, the Desalitech process is not built into the membrane projection, so you need to do a couple of iterations, but you get very accurate results with it. So another question, so what is the scope of application in nanofiltrations, NF applications, specifically for sulfate removal? So nanofiltration can, generally it's a more permeable RO membrane, very similar to RO in that it needs cross flow to operate. One of the initial uses for nanofiltration membranes was selective removal of sulfates from seawater for use in oil and gas applications, the famous marathon process. So, so that membrane, again, works just like an RO membrane. The advantage that the Desalitech process would bring to that application is, like in any other application, high recovery and low energy consumption. So a question about materials of construction for high TDS concentrate. Again, there's a lot of industry precedent and standard on how you manage high conductivity, high TDS waters. Generally for seawater applications, at least duplex stainless steel, if not super duplex, if not one of the high austenitic, high molybdenum materials. So we just use standard RO equipment, and it includes the appropriate metals and material selection for the TDS of the water we're working with. So another question about membranes, which membranes we're using. We've gone right down the line and used pretty much everything we've been able to get our hands on. So the FilmTech, Hydronautics, Torre, CSM, and Nano H2O. And Lanxess are the ones I'm aware of. We also have used nanofiltration membranes supplied by GE. And as I said before, they all pretty much perform according to their projections. So question about treatment of city water. So what would we expect for a recovery rate from city water sourced from wells? It really depends. So if you're getting city water from wells in the American Midwest, it's likely going to have all kinds of calcium and magnesium in it. And so the high hardness may limit recovery. Again, we talked about scaling resistance in a Desalitech system. You may be able to supersaturate, you can supersaturate calcium sulfate, for example, and therefore get to higher recovery rates in a Desalitech system than you would be able to with conventional RO. But what the performance is, how high a recovery rate you can go really depends on the specific water chemistry. We've, again, seen recovery rates as high as 98% on pretty good quality water coming into a Desalitech system. Other times we're limited at lower recovery rates. By scaling, you can adjust pH and use antiscalants in the same fashion that you would use them in a conventional RO system. So question about membrane life. Can we comment on membrane life in a CCD system, and would we expect to see a reduction in salt rejection over time? Yeah, so again, it operates a lot like a typical RO system. The more frequently you need to clean the membranes, the shorter their lifetime. So while cleaning restores membrane performance, it also takes a bit away in terms of membrane life. So in water reuse applications where you're looking at clean in place every 4 to 6 weeks, you might only get a year or two out of the membranes. In seawater RO, where there's maybe cleaning once a year and maybe less, 6 years is kind of the rule of thumb for seawater applications. And it would be the same with in a Desalitech system or in a conventional RO system. And then, yes, as the membranes age and wear out, you expect more salt passage and reduced permeate quality. So we've been asked to explain how we get a 60% lower cost of ownership. And generally it's because the cost of water for an industrial brackish water treatment, so the cost of the excess water you're bringing in, like let's call it tap water, and then the concentrate you're disposing, let's say to the sewer, that can be nearly 90% of your cost of ownership. So if we're able to raise recoveries such that we're reducing the excess water use by 75%, that's how you can accumulate an enormous savings. So I guess the question I passed inadvertently on was, what's our biggest challenge? What are our biggest challenges for large-scale systems? Generally speaking, large-scale RO applications are done with multiple trains. So for large installations that Desalitech is designed and built, we do have train sizes up to 1,200 gallons a minute. And that's about 1.5 million gallons per day, or about 300 cubic meters an hour. So we would build multiple trains to meet the capacity requirements of our customer. For any large RO system, of course, you need to find pumps large enough, valves and instruments large enough, but for the most part, you're still using 8-inch membrane pressure vessels. You just use a lot more of them. So it's the same in a Desalitech process. RO scales very well. All right, so what's the cleaning frequency of the elements? It really depends substantially on the water quality and how the membranes are operated. So generally you monitor normalized flux as a performance parameter, and it tells you as your flux drops, if it drops independent of the recovery rate, water quality, temperature, etc., you know you're getting fouling or scaling of the membranes. And then if you lose, say, 15 to 20% of normalized flux, it's probably time to do a CIP and recover membrane performance, and how frequent that is really depends. Okay, so there's a question. Normally we have a space or a blank in our housings. Is there a specific reason for this other than for not fitting? Is there? I guess the question is why don't we fill the pressure vessels with membrane elements? Sometimes we do. So, but for our general standard product design, we use 4 membrane elements in a 5M vessel. What that's doing is adding a little intrinsic volume to the system and giving us a little more time between flushings, or a little bit longer sequence time. So we found that that combination, 4 elements in a 5M vessel, covers a very broad range of recovery rates and water types. So that's why the extra space, but it's not necessarily required, especially if operating over 90% recovery. We can generally fill the pressure vessels with membranes. And in fact, we can use an 8M pressure vessel. So in that case, we would use have a pressure vessel with a center port, and it would contain 2 4-element arrays, one on either side of the center port. Okay, the question is, do we still apply anti-scalant? The answer is yes, and in fact, pretty much in the same way that you would for conventional RO system when you're driving to whatever recovery rate you're driving to. Sometimes we're able to get away with a little less anti-scalant, but most of our customers are trying to achieve high recovery. And they do that with a combination of our process, intelligent anti-scalant dosing, and pH adjustment. Yeah, okay, I'm going to take 2 more questions, and we're getting to the end of the hour here. So, does a CCD design work with effectiveness on smaller systems, 4 to 12 gallon per minute units? It definitely does. There's some loss of economy of scale in getting into small units because our systems all have control panels to drive the pump variable frequency drives and drive the automated valves. So a lot of times we're not as cost efficient on small systems, but we do have, for example, pilot systems that operate at 10 gallons per minute permeate output. All right, can we elaborate on how our technology is able to achieve higher recovery rates without scaling? And I'll take this as the last question. The slide deck does go through this to some extent, so I'd encourage you to look back over that. But generally speaking, what happens is that scaling is a 2-step mechanism. So scaling requires that salts be supersaturated, and then there's some time and conditions need to be right for the precipitation to actually occur. So that latter portion is called the induction time for precipitation. So again, you need to supersaturate and then allow for the induction time for scaling to actually occur. And what the Desalitech process is able to do is flush the system without giving precipitation enough time to occur. So we're working inside that induction time. So that's how we're able to trick scaling and we're able to operate at higher recovery rates with supersaturated concentrate. That plus the standard ways to avoid scaling in RO systems, which include use of anti-scalants, pH adjustment, good cross flow, etc. Okay, we're very happy to take more questions. So if you can, please email those to info@desalitech.com, info@desalitech.com. And I think David will talk to you a little bit more about archive of this presentation and additional resources for you.
Okay, thank you, Rick. That was great. And thank everyone for attending. So before you leave, there are 3 polling questions that Daryl is going to pop up. If you would just answer those, it's just doing 3 little clicks, but it gives us feedback on today's webinar. So again, thank you so much for attending, and we'll look forward to having you at a future webinar. Bye-bye.